Today we are going to look at binomial probability, and bi, think of that from the word, bi means two, and so binomial probabilities have two options with the same chance of outcome, and it happens or it doesn't. So characteristics of a binomial distribution: it has a specific number of identical trials. The trials are independent of each other, so outcome of one does not depend on the outcome of the other. The result of each trial is success or failure. That's the bi part of a binomial. And the probability of success is the same for each trial. So this is just some concept attainment thoughts. Which of the following can be modeled by a binomial distribution? A child rolls a die 10 times and counts the number of threes. So the roll of the die, the second roll has nothing to do with the first roll, so it is independent. I'm counting the number of threes, so I either get a 3 or I don't. So therefore, this is binomial. The first player in a free throw basketball competition has a free throw success rate of 88.4%. A second player takes over when the first player misses the basket. So the second player has to wait for the first one to miss a basket. Therefore, it is not independent, so it is not binomial. A farmer gives 12 of 200 cattle in a herd an antibiotic. The farmer then selects 10 cattle at random to test for infections to see if the antibiotic was effective. The probability of the cattle being injected with the antibiotic is not uniform, therefore it is not binomial. A factory producing electric motors has a 0.2% defect rate. A quality control inspector needs to determine the expected number of motors that would fail in a day's production. Every motor has the same potential for defect rate. The motor is either defective or it isn't, so therefore, so it's independent, same probability. This one is binomial. Probabilities of the number of queens in a 5-card hand. Once you draw cards, the second draw is now dependent on what you got for the first draw and whether or not you will get 4 queens in a 5-card hand. Therefore, it is not independent. Therefore, it is not binomial. Probability of each sum when 2 dice are rolled. Again, these don't have the same probability because now I'm looking at 2 dice, not 1. And so I'm looking at sums, different probabilities. This is not binomial. Lastly, the probabilities of the number of times a 5 occurs when spinning a spinner 6 times. Well, we're going to assume that the spinner is fair and equal, and therefore the probability of each of the spinner landing on each section is the same, and one spin does not depend on the other, so therefore it is independent, same probabilities. This is binomial. So here's the formula for binomial. So the event of interest is the probability of obtaining exactly x successes in n number of trials. So we have the probability of x equal to x, gives the number of trials, choose the number of successes, times the probability of success to the power of the number of successes, times the probability of failure, times the number of trials minus the number of successes. So it makes a little bit more sense when we put it into practice. So we've got the chance of success for the number of successes and the chances of failure for the number of failures. And then because the probability for all the trials are the same, the expected number for success in any one trial is p, and therefore the expected number of successful trials is just n times p. In this example, taking a quiz unprepared. A student is taking a multiple choice quiz. Each question has 4 possible answers. The student did not attend class or look at a textbook. He thinks he's going to guess. How likely is it for him to pass if there are 4 questions? Well, first of all, that means that he has to get at least 2 out of 4 to pass. So therefore, our number of successes, the number of them has to be 2 or more. So we're looking at 2 or 3 or 4. So n here, or the number of questions, is 4. Because there are 4 possible answers in each question, our probability of success is 1 in 4, and our probability of failure is 3 in 4. So we're looking for the probability that x is greater than or equal to 2. So the probability of x equals 2 plus the probability of x equals 3 plus the probability of x equals 4. So using the binomial equation, we have all the information that we need. So we will put together our probability equation. So when we do all the math, we say he therefore has a 26.17 chance of passing by guessing. In a family of 5 children, what is the probability that there are exactly 2 girls? So success in this case is the number of girls, and a failure is the number of boys. The probability of having each is 1 in 2. And so that's our P and our Q. And we have 5 children, and we want exactly 2 girls. So N is 5, and X is 2. Or we have a 31.25% chance of having exactly 2 girls. Now, what will be the probability of having 3 boys? So P, in this case, our success is now having a boy, failure is having a girl. Probabilities haven't changed, it's still half and half. N is still 5, but in this case now X is 3. So the probability of X equals 3. Or, oh wait, 3 boys and 2 girls. It's the same question, just asked in a different way. So we're going to prepare a table and a graph for a binomial distribution where our probability of success is 0.2 and our number is 5. So of course, if success is 0.2, that means that failure, or Q, is 0.8. So if I have 0 successes, that means I have to have 5 failures. And that's where these come in. Sorry, don't want to erase it. Right? To have 0 successes, I have to have, I have to have 5 failures. And the probability of success is 0.2, and the probability of failure is 0.8. And that's how those numbers come about. So I have a 32.7% chance of having no success in 5 trials with this particular experiment. So notice how, because I have a small chance of success, that the probability of me being successful once is the highest because 20% of 5 is 1. So that has the biggest probability. And then my probability of being more and more successful goes down smaller and smaller. So now we're going to create a histogram for this distribution. So as I make my squares for my histogram, you can see that when I get to the probability of 5 successes, I'm basically on the line. I have almost non-existent probability of that. So those are 2 of the possible ways to show a probability distribution. With a certain set of atmospheric conditions, the probability of rain is 40%. During a 1 month period, 8 days had these conditions. What is the probability that it rained on more than 6 of those days? So even though we're talking about a month, I am only talking about 8 days. So n equals 8. I'm asking if it was possible for it to rain on more than 6 of those days. So more than 6 is not 6 or more. So that means that x is greater than 6. So I'm just looking at the probability of it raining on 7 or 8 of those days. The probability of success is 40% because that's how much the percentage is for it to rain. So the probability of failure is 0.6. And now I'm going to put that into my formula and figure out what the probability it is that it rained on more than 6 of those days when there was only a 40% chance of rain. So rather than show all those calculations, because it is a lot of very small numbers, our answer comes out to 0.008519, or there is a 0.85% chance of rain on 7 or 8 of those days. Now, what is the expected number of rainy days? So this is just where we take 8 and multiply it by the probability of success. So that means that given a 40% chance of rain over 8 days, we're going to expect about 3 days of rain. I'm slightly out of order here. I've just had a technical difficulty, so we're just going to drive forward. 6 people are asked to choose a number between 1 and 20. What is the probability that 2 people choose the number 9? What is the probability that at least 2 people choose the number 9? So we'll look at that in 2 different ways. First of all, the probability of people choosing the number 9 is 1 in 20. The probability of people not choosing the number 9 is 19 in 20. We've asked 6 people, and we want to know if exactly 2 people choose the number 9. Or therefore, we have about a 3% chance that 2 people choose the number 9. Now, at least 2 people choose the number 9. So now we have to see what is the probability that x is greater than or equal to 2, which is a lot of numbers for 6 people. So rather than do all of that math, we are going to use the indirect method. So we're going to look at the probability that x is less than or equal to 1. And then we will subtract that probability from 1 using the indirect method. So that means that there is a 96.71 probability that 1 or no people will choose the number 9, which means that using indirect method, the probability of x being greater than or equal to 2 is 1 minus the probability of x being less than or equal to 1. or a 0.0329, so it's a 3.3% chance of more than 2 people choosing 9. World Cup. It is estimated that the best goalie in the world has a 15% chance of stopping a penalty shot. That means there is an 85% chance that there will be a goal. The best shooters in the world have a 12% chance of missing the net, which means they have an 88% chance of making a goal. So we have to combine those two probabilities to get our probability of success of getting a goal. And then, of course, our chance of failure is 1 minus that. So the chance of both the goalie stopping the goal and or the shooter missing the net is 25.2%. Now we figure out, so the probability that one shot will go in. So we're looking for the probability of x equals 1. So that means that there is only a 1.5% chance that only one shot goes in. So if we create a probability distribution table for the number of shots scored, we're going to look at x equaling 0 through 5. So of course, for 0 shots to be scored, we have to have 0.4748, to the power of 0, and 0.252 to the power of 5. So that all the way down to 5 shots scored on goal and no misses. So there is our probability distribution. Now, what are the expected number of shots that will be scored on goal from 5? So that's just the number of shots times the probability that the shot would go in. So therefore, we are expecting that between 3 and 4 shots will be scored on goal. And if you look in the distribution table, that is where the highest probabilities are. So now is the time for you to go and do some practice.